wish you all very, very happy New Year. We are on the tarmac of Flight Laboratory airstrip, and you could see that I am surrounded by so many aircraft, and similar aircraft you might have seen when you did the performance course. But it's a customary that I introduce all the aircraft to you because I do not know really how many students have done this course, first course, which is a prerequisite for second course, that is on stability and control. So let me explain you whatever aircraft we have with a specific impetus on the components which will be used for, very useful for stability and control understanding. This is Cessna 206 airplane. Here you could see the wing is again a high wing configuration, and these are the struts to support the wing. And in performance course, you know what is this propeller is meant for. The propeller has a unique role to give power, extract power from the brake. But in performance also we decided that, we understood that, to be more precise, that wing is meant for giving lift. It has nothing to do with stability because we assumed during performance analysis the aircraft is both statically and dynamically stable. Okay. So in performance course we are more bothered about what is the lift generated by the wing, what is the drag generated by all the components, lift by all the components, and we are primarily aiming towards an L by D, which is maximum, right? Now, but in this course, we will be talking about stability and control. So our focus will suddenly go towards this portion, which is called horizontal tail. This is completely horizontal tail, and this horizontal tail will be seen, and you will understand now that this is primarily responsible to give the longitudinal stability. Okay, and you could see the part of this horizontal tail can be moved up and down, and this is called elevator. It also has a trimmer which goes up and down in the opposite direction, and we'll discuss about what is the trim tabs will be doing. Most important thing to understand is this total area, both sides together, is responsible to give both static and dynamic stability in the longitudinal plane, and part of it, which is called elevator, is responsible to give the longitudinal control. That is, if I want to move the airplane up and down, I will be using this elevator. Okay. Similarly, it has a trim tab. You could see here, I don't know whether it's visible to you or not, the small portion which is required to use at the end so that pilot can fly hands off. We'll talk about that. Okay. Similarly, if you see here, there is a vertical tail which gives you stability in terms of directional and lateral motion. And part of this is called rudder, which can be moved either way to turn the airplane this way or that way. So that is the rudder control. So we have now elevator control, rudder control, and now we'll go for the aileron. So what is the role of elevator? If I want to pitch like up and down like this, I'll be using elevator. So it is an elevator control. If you want to move the airplane yaw in this direction, then this is a rudder. Okay, so rudder control. If you want to roll the airplane, bang the airplane like this, then this control is called aileron. So if I move it down like this, you could see as it goes forward, force will be acting upward, and it will give the left wing will go down. Similarly, if I put it like this, other thing, it will bang like this. So this is called aileron. There will be another pair of aileron on that side. So you can move it together, you can move it differentially. So this is called aileron or aileron control. So we have now three primary control. One is elevator for longitudinal control, rudder for directional control, and aileron for roll control or lateral control. These are the primary three control surfaces we'll be using, and when you are defined everything about stability, we will also try to see how this control forces or moments generated gives a response vis-a-vis the stability characteristics of the airplane. Okay, so that will be the total part of this, one of the module of this course. And I'll be flying this Cessna 206 with my pilot and also giving you a live demonstration of what is the meaning of static stability or dynamic stability in flight. This is our Hansa 3 aircraft. I'll be walking down to Hansa 3 aircraft, which is our nation's pride, one of the finest lightweight aircraft. You could see that if I compare Cessna 206 and Hansa 3, you could see this wing is a low wing, it's not a high wing configuration. So from stability and control point of view, this thing will have implication. That is why I am stressing you, please keep back of your mind. So Cessna 206, which I showed you just now, has a high wing configuration, and this is a low wing configuration. Okay. Similarly, we have, this is Sinus, manufactured by Pipistrel. This is called motor glider. Motor glider because conventionally gliders were launched by a cable winch combination, right? It is like flying a kite. But nowadays you find the gliders means high L by D ratio, right? So that they can loiter for longer duration. But you need to take off. So instead of cable, what has been done, a small engine has been put. So that is used for takeoff. Once you go to a particular altitude, you switch on the engine. There are gliders where the whole propeller will go inside, so that you have a very good L by D configuration. You fly, and then when you find that it has come down to a lower altitude, you will still engine, start the engine and go to another altitude and glide. So you have a very large endurance from that perspective. This glider, if you see, also has high wing configuration. So from a stability and control point of view, you please note down that there must be some requirement to have high wing consideration, sometimes low wing consideration, and primarily from a stability and control point of view, and sometimes it could be because of maintenance point of view also. So we'll be talking about those things in detail, okay? And since I'm talking about the gliders, I've talked about Hansa 3, the speeds are less than 0.3 Mach. You could see this is these are the aileron, which by now you know, and these are used to give a bank to the airplane. Airplane can be rotated like this through this aileron, and this is also one of the controls. Like we have elevator, we have a rudder, and we have aileron. Okay, these are extremely important to understand, because please understand, in this course we are not going to talk in terms of performance, we are going to talk in terms of stability and control. So we'll be really bothered about how much moment each component gives about center of gravity and whether that contributes to static stability or not. That's very important, right? For example, if you see this airplane, right, and if we assume that, let's for a fictitious way, we assume that CG is somewhere here, let's say here, okay? Let's say, hypothetically. So if these wings see some angle of attack, its lift force I can represent at the quarter chord point. So this force will give a nose-up moment, okay? As angle of attack will increase, this will give nose-up moment. That means with increase in angle of attack, this wing will contribute towards this stability, because it will further take the aircraft up. But if you see the tail, since CG is there, if there is a change in angle of attack, then this will have a force in this direction that will give a nose-down moment. So this will try to reduce the angle of attack if there is at all given through a disturbance, right? So this we will be talking, it has some sort of a stabilizing effect. All those things we will be discussing. In a general, you'll find that any component which is located ahead of center of gravity will give a destabilizing effect. Any component which is behind center of gravity will give stabilizing effect. So this is in general, we need to understand seeing an airplane, and then we will be talking in detail and formulate it and try to see how can I understand these characteristics and configure an airplane with a adequate, well-planned and designed stability characteristics, right? That is the basic purpose of this course. So we are talking about low subsonic or low speed aircraft. Now in this course, as far as stability and control are concerned, we will not be restricting ourselves to low speeds. We'll also go for higher speeds. So let me introduce one of our another pride aircraft. I have the model for that aircraft, and you all must be knowing this is Tejas, right? This is a delta wing configuration. This is one of our pride Tejas subsonic aircraft, and it has a delta wing, lot of sweep, okay? And you could see control surfaces are laid in a different manner than what is in a conventional aircraft. In performance, when you are talking about sweep, we are talking in terms of critical Mach number, primarily to reduce the drag. However, once the sweep or such high-speed airplane is there, we need to discuss about what is the effect of speed on stability, what is the effect of variation of parameters with speed in terms of dynamic stability, then what is the sweep is going to do as far as stability and control considerations are there. So that's why this Tejas, which I am purposely showing you, I always love to show our own aircraft. Unfortunately, out of so many aircraft, only 2 are our own aircraft. I would like this sort of a course should help our youngsters that after 10-15 years, this tarmac is full of aircraft designed and manufactured by India only. Okay, with that aspirations, with that wishes in the new year, I again say Happy New Year to all of you, and let's start learning this course with a clear-cut ambition. The next 10-15 years, this tarmac will be full of aircraft manufactured, built, designed by we the Indians. Thank you very much. We are back again, and Kanpur, it's basically a pleasant part of the winter session. You will find during this time, people are wearing fancy dresses, warm clothes, lots of fog around, lots of disruption in flight, but there is a tacit freshness among all the individual. With that freshness, we will start this course titled Flight Stability and Control. And I will underline 2 words, one is stability and control. In my first course on airplane performance, at the end, we have discussed about these 2 terms, stability and control. In this course, we will start from there, but now we will be unfolding few salient things in an exhaustive manner to understand the true meaning of stability and control and how a designer will ensure the stability and control aspects of airplane so that finally the pilot who is flying at ease. Do not forget, whatever you design as a flight vehicle, if it is a manned flight vehicle, we need to be bothered about the human being, the pilot, the passengers. We should be very, very careful about their comfort. If they are not comfortable, then the vehicle is not well designed. To ensure that we take care of these issues, we need to know more detail about stability and control. Now the question comes how I am going to take this course forward. See, in introduction to airplane performance, we were talking about mostly a response of the airplane in terms of translatory motion. So we assume that, yes, we will apply Newtonian's law, that is force equal to m into acceleration of center of mass. So we simplified our whole description through a point mass approximation or point mass model. But in this course, since we are talking about stability and control, we will be talking about not only how the airplane is going in a transitory motion, we also like to talk about is rotational motion, right? And the moment something rotation comes, your point mass approximation or point mass simplification will not work, because you know in rotation it is not the total mass, it is the mass distribution, or we say it is the moment of inertia that plays a role. Okay? At the same time, we will be also bothered about what is the moment coming on the airplane at a given flight conditions. Since these things we have touched upon in last lecture, so you will find that few of the last lectures will be repeated so that there is a continuity. Why that is important? Please understand, after all, we have learned by now some important phases of airplane motion, and this part was taxiing and takeoff. This was climb, this was cruise or it could be accelerated flight. This is loiter, and here it is landing. The question we ask ourselves is, if I want to climb, I need to generate particular amount of lift, and once I generate particular amount of lift, how do I generate? That is, what are the control surface I deflect? And that part is taken care in the topic of control. And the next question comes to our mind, if I deflect the control, let's say elevator, whether the airplane is going to be stable or not. Or, to be more precise, more correct, how this control deflection will generate a response to an aircraft which is stable. Same control input will have a different type of response if the aircraft is not stable, right? So we need to build a relationship between stability and control in a very tacit manner, and we should understand exactly what it means, what this relation is going to give us. For example, so far we have assumed that for a cruise we have to give some elevator deflection, but question is, if I give an elevator deflection, does the airplane immediately comes to the angle of attack, or there are transients? And if we want to really design an airplane, better we should know clearly about their transient response. So that is the part of a stability, which is we refer to as dynamic stability. Okay? So in stability we'll have static and dynamic, both. Okay? And by control here we will be primarily meaning this elevator control. It could be aileron, there could be rudder, there could be canard, like this. So we'll try to understand each of these and try to see how stability and control are connected. How they are connected, and why we are interested in how they are connected, because finally we know through their relationship what is the handling qualities of the airplane, because we are more bothered about the pilot and the passenger. Okay? So that will be the whole direction, roadmap for this course, and we will be taking you back to our earlier lectures, maybe around 8 to 10, where we'll start the introduction the way we used that time, so that there are continuity. Okay? I'll use the Man Ki Baat too frequently in the first 15 lectures, so as to ensure that we are seamlessly going into a direction where the continuity is there. Okay? Let us go back to this term stability. And we agreed that we will try to study it through static and dynamic stability. Okay? What is static stability? If you recall, we are clear by now through our first course that every system which is in equilibrium, or any system which is in equilibrium, and if it is disturbed about the equilibrium, and if it has initial tendency to come back to that equilibrium, we say the body is in static equilibrium, or the body is statically stable. We say the body is in statically stable. That is precisely more correct, appropriate. Just to recall, remember, we have given this example I draw this line. This is a ball. Now what happens? It must excite your mind to go back to your class 10th, 11th, where these diagrams were frequently used. We say this body is in equilibrium. This dotted line shows the equilibrium position. What is the meaning of being equilibrium? The net force and net moments are zero, right? The similar case, if I come to aircraft, one of the equilibrium state is when the airplane is in cruise, okay? Where lift equal to weight, thrust equal to drag, net force is zero, net moment is zero. So cruise is also an equilibrium state. Now what is the question we are going to address? We are going to address whether this body at this equilibrium is statically stable or not. Meaning thereby, if I come back again from here to here, if I have the same question, yes, this body is in equilibrium here because net force is zero, whether this body is statically stable or not, how do I check? I say I give a small disturbance. The moment I disturb it from the equilibrium state, you see there is a component of weight or will be there which will try to take it back to the equilibrium state. So it has an initial tendency to take the body toward the equilibrium state. The catchword is initial tendency. So you say this body is indeed in statically stable mode or statically stable condition. In contrast, if you say this body here, if I displace it by small amount, now the component of weight will take it away from the equilibrium state. So we say it doesn't have any initial tendency to come back to equilibrium, so this is statically unstable. This is clear? Similarly, with this understanding, if I try to know whether this gentleman, our friend aircraft, is statically stable or not, what we have to do? We have to first see what is the equilibrium state, because static stability, we are talking reference to the equilibrium, a disturbance about the equilibrium. So first we find out the equilibrium state. Here I know the cruise, where lift equal to weight, thrust equal to drag, and moments are automatically balanced. This is typically an equilibrium state. And now, if I want to check whether this is in static stability or not, satisfying static stability conditions or not, what I have to do? I have to give it some disturbance, say delta alpha, angle of attack, maybe an upward gust coming like this. And if it immediately generates a moment nose down, that is to nullify that delta alpha, because initially the equilibrium state was, let's say, alpha 2 degree, and because of a disturbance, let's say angle of attack became 3 degrees. So static stability demands that it should automatically generate a nose down moment so that it has initial tendency to come back to 2 degree of alpha. Is it clear? Okay. If it has, it is statically stable. If it doesn't have, it is statically unstable. At this point, please understand, it is not that we cannot control a statically unstable airplane. The catch statement is unstable doesn't mean uncontrollable. You can do an experiment. You can take a stick on your finger. Imagine a stick is there. It's statically unstable, but you can control it. Okay? In fact, most of our fighter airplane, they are marginally stable or marginally unstable in terms of static stability sense. That is why they are highly maneuverable. Okay? Once we do the static stability, we will be spending a lot of time on dynamic stability. That is, okay, fine. We understand that. Suppose I take a mass spring system, right, and assume that this whole mass spring system is isolated from the environment and the spring is linear, there is no air, there is completely vacuum. You know very well at some point this is the equilibrium. That is, here, if I draw the free body diagram, I'll find mg acting here and here, the force because of extension kx, and they're balanced. So it is at equilibrium. Now, if I want to check whether this body is statically stable or not, what I have to do, let's say I stretch it. I stretch it here to some length and then release it. So what will happen? The moment I release it, because there will be a force kx acting opposite, so it will start moving towards the equilibrium. It will overshoot. Again, as it overshoots, the force will be acting downward, so it will again take it like this. So it will go on oscillating like this. And since there are no air, no medium, as spring is linear, it will keep on oscillating like this. So do you call it statically stable or not? Let us check. From the equilibrium, when I am deflected the body, it is tendency to come back to the equilibrium, so it has initial tendency to come back to the equilibrium, but because of inertia it goes up. Again, as it goes away from the equilibrium, it has a tendency to come back to this. So it goes on doing like this. So it does have static stability. But does that mean it has dynamic stability? If you want to know what is dynamic stability, we have to put another condition, that not only the initial tendency to come back to equilibrium, but also the amplitude should decay in finite time. That is, it should go on doing like this, and finally it should come here to equilibrium. So this will not happen here. This is a case where it is statically stable but dynamically not stable. Now think of a situation, if I put some water or oil into this, what will happen? It will have this, and amplitude will come down. So there is a damping. And for dynamic stability, not only the initial tendency, it should also, its amplitude also should decay in finite time. So there will be a concept of stiffness, there will be a concept of damping when you are talking about dynamic stability, right? And this damping decides the passenger comfort or the handling qualities of the pilot. So we'll see how they get connected. Okay. So we'll be talking more and more on the dynamic stability in this course. Few part of static stability we have covered in the last course, because there will be many students who will be joining this course who may not have the first course exposure, or even if they have, it may be one time. So it's my duty to see that we revisit again important points, and we make you prepared, ready to cruise or accelerate into the stability aspects, including dynamic stability aspects. This is one thing. Second would be the response. That is, if you see, let me erase this part. Suppose this is the airplane, and this is the tail, and this is the elevator, the wing, and there is a rudder, and there is an engine. Let's say it's flying, some speed. We have seen whether it is statically stable or not, dynamically stable or not. Once we have done that, then we'll try to know if I give unit deflection of elevator, how the angle of attack is building, right? Say whether it is building something like this, or building something like this, or building something like this. So in the three diagram I have shown that they are all finally coming to some angle, let's say alpha star. But this three graph also tells you that transients of going to that alpha star is different. So we have to clearly see how do I calculate alpha star, that the response for a deflection of elevator in time domain, right? With time, how it is happening. So this is also extremely important topic that we'll be discussing in this course. So you could see that initial few 8 to 10 lectures will be exactly what we have done in our last course, In fact, some same video clips will be shown to you. I'll be coming again after 2 or 3 or some lectures as a Mann Ki Baat session and try to discuss few things more, because there will be many students who might not have done airplane performance, or even if they have done, they have missed few concepts. But once we build a solid base, then we go systematically into static stability, what are the control required, dynamic stability part, response, and how do I design the handling qualities. So this will cover the whole course, which is, it's a huge course, please understand. It will require little bit of effort from your side. You have to sit with pen and pencil and solve some equations which are, again, not more than a first degree equation. Maybe sometime I'll be using Laplace transform, which I'll explain. Don't get panic about all these names. I will ensure and take guarantee that it will be as simple as if you are a student of class 12th or at the most first year. So with that positive note, we will take up this course. I hope you will enjoy, and this time for a change you will be allowed to interact with me directly on question sessions through my another email ID I'll be creating, but I would like to interact with you directly along with the TAs, right? So that helps, that sometimes there is a lag which I learned from last course. Thank you.